So we talked about Brown-Erdos-Sos conjecture, and one case that's known was 6-3 theorem. And what is the Brown-Erdos-Sos conjecture? It conjecture that this one is zero of n square. So meaning that whenever you have assets, they spend more than this number of vertices, then you show that that conjecture says that it must have a subquadratic number of edges. And yeah, we show that this N63 is known to be at most 0 of n square. And okay, maybe let me mention about the size of this. So if we see we use the removal lemma to prove this, and then you actually try to get the quantitative version, then you can get the upper bound, and from that you can deduce some upper bound. But there are slightly better bound known. So if it's known that it's at most this number, and at least this number. So again, this one comes from the balance construction. It's essentially, same. So using the construction, you can show that this lower bound holds. And for this upper bound, what's this log star? This log star is like inverse of the tower function. So this is the number of log you have to take to obtain n to obtain a number less than 1, less than or equal to 1. So what does it mean? If you have say 10 to the 10 to the 10, or say e to the e to the e to the e, then you take a log, then you get e to the e, and you take another log, and you take a log, and you take a log. So how many times you take log? 1, 2, 3, 4 times. So log star of e to the e to the e to the e is 4. So that's this log star. And best, if you just use the removal lemma, then your bound you get is essentially this one. You can get the upper bound on this by using removal lemma. And but the box used another version of removal lemma to get this upper bound. So that's the best thing we know. And this 6-3 theorem has many applications. For example, there is, in computer science, there is this theorem called PCP theorem. And that's in computational complexity theory, one of the big theorem. And there, for proof of that theorem, there was, some part of it requires some efficient test for testing for a function to be Boolean function or not. Boolean function needs to be linear or not. And there, Shakespeare theorem was used, and yeah, some other applications as well. Okay, and so this was conjectured, but it's not known except for this one case. But there are some partial results, some weaker results. So for example, Sarkozy and Perko 2005 proved the following weaker bound. So it says that S edges spans more than this number. But if we make it even stronger, S edges span more than this number. So this is bigger than or equal to this. So when S equals 3, then this is what? This is 1. So it's same. So that's exactly this case. But as S equals 4, then this is 2. So this is the same number plus 4. This is the same number plus 3. So this is weaker bound than the conjecture. But this can be proved. So how do we prove it? So we consider an R graph H with say epsilon n square hyperedge. And we take a R partition such that say B1, B2 to PR such that at least R factorial over R to the R times epsilon n square edges are between these R parts are intersecting all R sets at one point each. So we partition it. If you have an edge which uses 2 vertex from here, 1 vertex from here, then we delete. We only keep the edges which use 1 from each. Then such partition exists. Why? You take a random R partition, and then you consider the expected number of such edges. And you get this expectation. That shows that there must be a choice which does at least as good as the expectation. That provides you this partition. Then what? Now we want to reduce our problem by considering shadow graph. So consider the 3-partite shadow 3 graph. H prime on the first 3 vertex. B1, B2, B3, such that its edges are triple, which are contained in edge in H. So again, shadow graph means that whenever you have an edge, you take all possible subset of the right side inside of the edges, hyper edge, and then for that uniformity, you consider all possible subsets and you replace. So when you have 5 vertices here, then you consider all 3 subsets, and then you put that as your edge. Then you get this 3 graph, and then you restrict your attention between these 3 sets. So So what we know is that the most f edges of H corresponds to the same edge in H prime. So in H prime, this triple may come from more than one edge. But if you have a three vertices which come from F many edges of H, what happened? Then there are R set, R set, R set, R set, which are all hyper edges in H, which intersect at 3 points. Then what? They span. Otherwise, we have, say, F edges in H on at most R minus 3 times S plus 3 vertices. A contradiction. Our assumption is that this H satisfy this property that the F edges and more than this edges, this vertices. Then what? This provides a lower bound on the number of edges. So R factorial over F times R to the R epsilon n square. But the point was that this is still some positive number. And n is sufficiently large compared to this number. And now what? Similarly, we again consider graph G, shadow graph. G on the first two vertices, B1 and B2. No, let's say B2 and B3. With the same definition. So BW is B2 and B3. If there is U in B1 such that the UBW is an edge in H prime, and we put it. Okay, now what? Now we reach vertex in U. We consider the M sub U as a collection of all edges in G, which come from this U. The U is here, and then you consider all the edges, and then you take these edges as a matching, as a M sub U. And by the same logic, you again shrink the number of edges by at most F. Otherwise, you get, if F of them give the same edges, then yeah, you are happy. You get the contradiction. Then what? Now the following claim. So for any, say, C and C prime, let's write it this way. So it is the following. So if n is small and eta is also small, then so n and eta are sufficiently small. If he is on n vertex graph with the number of edges being at least C times n squared, and this edge is Okay, maybe before this claim, let me characterize that. So for each u, you can consider the edges of G, let's say GU, say EU, with PW such that the UPW is an edging here. Okay. Then here, what do we know is that this gives the graph, but the maximum degree of this is at most f. Otherwise, what you have? U, and then let's say this B has maximum degree more than f, then you get this configuration, so S of them. So all S of them shares two vertex, and each triple was a subset of some other R uniform edges. And altogether, you get the S edges, which shares two vertices. That gives us at most this number of vertices. So S edges share, and this many vertices, which is contradiction to our assumption. So we assume that S edges covers more than this many vertices, so which is a contradiction. So this has at most size, maximum degree F. So we can choose a matching, say MU, which is subset of EU, with the size of MU being at least 1 over F times size of EU. Okay, then now let's say your new graph G. Now you take the union of them. So let G prime be the union of this MU, where U is in P1. Then this graph still has, you can see that like this number of edges. Okay. So now we show that the following claim holds. So when you have a graph, let's say this is the graph that you want to apply, and it has Lhasian sphere edges, and this is the union of C prime and many edges of the matching. For some matchings Mi. Then there exists some I and two sets, A and B, which is subset of the vertices on this matching of size eta n, such that the following hold. First, between A and B, it contains no edges in Mi. And two, there are still many edges between A and B. So we can prove this claim using regularity lemma. How do you prove? I will not write in full rigorous detail, but so you apply regularity lemma, and you get this regularity partition. And then what you can do is you initially the graph has density 2c. So this is at least 2c times n choose 2 edges. That means you should be able to find the regular pair, epsilon regular pair with the density at least 2c. So which is not difficult to show. I mean, if all of them has a density smaller, instead of 2c, let's say 1 minus epsilon times 2c, so at least c. So if all the regular pair density is below c, and all the non-regular pair, the number is smaller, then you can conclude that your entire graph has density smaller than 1 plus c epsilon times c, but the assumption is it has density at least 2c. So this pair is there. So you should be able to find one such epsilon regular pair. And once we have this, then what? This set has size much bigger than eta n. So this set size like at least 1 over epsilon times eta n. Why? Eta is much smaller than c and c prime, and you choose epsilon so that the epsilon is smaller than c and c prime. And then this is much smaller than, say, 1 over t, and then much smaller than eta. So you can write it this way, and then make sure that the number of parts you have is at most t. Then this is size much bigger than eta. And now what? Here its density is at least c. So using Peter's principle, so there must be some matching mi which have many edges here. Then what? You just many edges in a sense that it has at least, like this is vi, vj. You have this condition. So at least c over c prime. So c prime many and edges. Not then vi edges here. And then what you do? You take this set as A, this set as B. So you divide the edges into half, and then you take the left vertices here to get A, right vertices to get B. Then each of them has size at least like C over C prime times N over R, which is bigger than eta n from our choice. And due to epsilon regularity, this set has size not so small compared to this, not so small compared to this. So between there are many edges. Using the definition of epsilon regularity, so you obtain this. And from our choice, the first one also holds. So that's basically proof of this claim. I will not write it in rigorous way. You will take some number of pages. I mean, some number of lines and leave. So what do you do? We repeatedly apply this claim to the graph G prime between the V2 and V3. So let's say they are A0 and B0, where A0 is B1 or B2. B0 is B3. Then what? You apply this, then you get A1, B1, and M, say U1. Satisfying these two conditions. And then you use this as your new C, and then C prime is same, and then you apply again, then you get what? A2, B2, MU2, etc. Then how does this look like? You have a A1, E1, and ready? You have a MU1, and you have many edges between here. You have A2, B2, and MU2, and A3, P3, MU3. So you get this way in nested manner. So we repeatedly apply, we repeat this until we obtain the 1 plus the log of x many matching. Then what? Then MU1 union with MU2 union with MUL forms a forest. So how does this look like? You have the one blue thing, and then you have red and red, and at the end of each red you have a black, 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 black. You have this manner. So each component looks like this. So you see in each component there are 1 blue edge, 2 red edge, 4 black edge. And if you want to do one more time, so purple, purple, and here, then how does it work? You have 1 purple, and it's rotation to do 2 blue, and in blue you have red, 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 red. You have black, 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 black. And here you have this forest, and then you choose a component containing a vertex in AL union BL. And it forms a tree with 2 to the L minus 1 edges, which is at least F edges. So 1 plus 2 plus 4 plus 8 is 2 to the 4 minus 1. Then what? We choose FH3, T prime, sub 3, then those edges of T prime, they corresponds to S hyperedges. in H prime, depending subset of what? The vertices in this T prime union with U1 to UL, so which corresponds to this color. So purple one actually corresponds to U1 in V1, and this blue one corresponds to U2, red corresponds to U3, and black corresponds to U4. So in H prime, these are the vertices. And how many? Having at most F plus 1 plus L vertices. Again, this was 3 uniform hyperedge, and then if you extend it to R uniform, then this yields a collection of edges in H covering at most R minus 3 times S plus 1 plus L, which is L at most this vertices. That's we want. Here the point was that there are many, almost half of the edges sharing one same color, meaning that you have U1, so they form an edge, they form an edge, they form an edge, and they form an edge, and so on. And next one also like quatermany with a red one. Maybe let me use the black color. Up until to here, your edges were like not cluttered, but these vertices, at this vertex, many edges cluttered, so it spans not too many vertices. If you actually see, if you just do 2 steps, then what do you get? So these together with this. So that's usually 6-3 configuration. Triangle, triangle, triangle. So this actually implies F3 theorem when your F here is 3. Okay, and yes, this is what we prove. And this was further improved by Conlon, Kishiboliner, Evanzov, Tapira in 2022, that they obtain additional log term on the bottom. So they reduce the function. And another direction of research was improve this into, smaller one. So this just said it's subquadratic, but it doesn't say how fast, how small it is from the quadratic function. So recently, Stenzer, Metsuku, Milojevic, and Studakov show that if we add some numbers here, then you can even show that this is strictly smaller polynomial for some epsilon. Okay. Okay, so maybe I will break the video here. And so we have talked about the Brown-Erdos-Sos conjecture and some partial results on the conjecture. Okay, thank you for listening. I will see you in next video again.